Good evening, everyone. I'm Rohit, working under the supervision of Professor D.D. Sharma in SSU IISc. I'll be talking about reduction in band gap with retention of ferroelectricity through heterovalent co-doping in barium titanate. So let me first start with the basic mechanism of PN junction photovoltaic uh, solar cell, which utilizes sunlight, of course, to generate electrons and hole pairs inside the material, and thus converting solar energy into electrical energy. These electrons and hole pairs generated are needs to be separated and collected near to the electrodes at the opposite sides to generate an electrical signal. Now, the mechanism by which this solar cell works is because of the built-in potential that is near to the PN junction, which helps in separating the electron and hole pairs which are present near to the junction. But those electron and hole pairs which are away from the junction do not feel this effective strong potential and therefore are separated less efficiently. And the band gap and the photo generated voltages that are generated by these solar cells are limited by the band gap of the material we use. In this regard, ferroelectric materials uh, are better because fundamentally the mechanism is different in the sense that the built-in potential in ferroelectric materials is due to the inherent polarization that is present, which runs entirely across right through the material and therefore leads to efficient charge separation. Also, one can generate above band gap voltages while using these ferroelectric materials. The problem that comes with ferroelectric materials is that most stable ferroelectric materials available today are perovskite oxides having AbO3 structure. Now, perovskite oxides come with a wide band gap, which restricts their maximum solar absorption. Now, to use ferroelectric materials as for photovoltaic purpose, one has to decrease the band gap. Now, most viable approach is to use a single head-to-end substitution at the B site of the perovskite structure. But these single heterovalent substitution mostly create oxygen vacancies or generation of holes in the system to maintain the charge neutrality. And it has been long known in literature that such substitutions have led to rapid loss of ferroelectric properties. So one then goes with isovalent substitutions at B site. Let's for the present study, we chose barium titanate as the host material, which exists in tetragonal phase at room temperature having P4 space group. Now, let's say one does an isovalent substitution of manganese 4 plus at against titanium 4 plus. This substitution leads to the phase transformation from tetragonal to trigonal, and therefore in the centrosymmetric space group R3 bar M, which is no more ferroelectric in nature. To overcome that, we devised an average isovalent substitution strategy, or I should say a co-doping strategy, to use a metal atom of valency less than 4 plus, say M1 3 plus, and another metal atom of valency 5 plus, which is one more than 4 plus. And candidates can be chosen as manganese 3 plus, iron 3 plus, and M2 5 plus candidates can be chosen as niobium 5 plus, not shown here, and tantalum 5 plus. The benefit that comes with such a strategy is that certain compositions can be stabilized in ferroelectric phase at a certain doping level. So using this strategy, Shyamashis Das et al. From our group designed a lowest band gap ferroelectric material by using a manganese and niobium pair and contrasted it with iron and niobium pair. Now one can see from the following data that the band gap for manganese and niobium doped barium titanate is reduced to a very considerable large extent as compared to the iron niobium pair, which is around 2.5. Also, this strategy led to the retention in ferroelectric polarization to largely to 70% of the inherent BTO, inherent barium titanate, I should call it. And the reason that is for such a usefulness of manganese 3 plus and niobium 5 plus pair as compared to iron and niobium pair was accounted to Jahn-Teller activeness of manganese 3 plus ion. In this, carrying forward the work, what we did, we chose copper and tellurium as our co-dopants and carried out density functional theory analysis for this dopant in barium titanate. We chose copper and tellurium because copper 2 plus is has a size of 0.73 angstrom. Tellurium 6 plus comes with a size of 0.56 angstrom, which is near to the average size of titanium 4 plus, that is 0.60. We chose the experimental lattice parameters for the unit cell to be A equal to be 3.992 angstrom and 4.033 angstrom. We considered the unit cell and optimized the internal coordinates. The titanium oxygen bond lengths after optimization came out to be 1.885 angstrom and 2.148 angstrom, which matches with the literature. Using this optimized lattice unit cell for barium titanate, we created 6 symmetry distinct supercells of size 3 cross 3 cross 2 and where we replaced 2 titanium atoms with shown in blue over here with 1 copper and tellurium, copper shown in pink and tellurium in green. Now, since 2 titanium atoms have been replaced amongst 18 of them, it accounts to an 11% co-doping concentration of copper and tellurium. We individually relaxed all these supercell configuration and examined the local distortions in all of the configurations. Right now, I'm taking an example of configuration 3. Now, if one sees in such a configuration, one finds out a local distortion. Let's consider TiO6 octahedra in all of these 3 configurations of MnNB, FeNB, and copper tellurium, which is present work. One sees that there is a finite off-centering that is present in TiO6 octahedra because of shifting of titanium atom from its centrosymmetric position, as can be seen by the asymmetric bond lengths in above 1.89 angstrom and below 2.15 angstrom, which is pretty consistent in all of these 3 co-dopants. Now, if one goes to tellurium in niobium and tellurium, that is the other co-dopant, one finds that in case of niobium, the both manganese niobium and iron niobium, there is a considerable off-centering in the C-axis. But in case of tellurium, one finds a non-polar distortion, not an off-centering, in contrast to the manganese and niobium and iron niobium. Next, if one sees the manganese and copper octahedra, one sees that the axial directions are way longer than the equatorial ones, seeing that Jahn-Teller activeness is present at the copper site and manganese site. But since iron 3+, which is a D5 system, is not Jahn-Teller active, and therefore there is no distortion at iron octahedra. So this work established the efficacy of using copper and tellurium, which helps in retention of these non-polar polar ferroelectric distortions. Now, saying that ferroelectric distortions are sustained in the system after a doping strategy of 11%, we set out to find the band gap of the system. For that, we found density of states. For pure barium titanate, it was found to be 1.67 eV, and the insulating band gap was found shown in the vertical line in the brown color. But for all the configurations we studied, we found that metallicity, finite density of states were found above Fermi level, showing metallicity in the system. This can be understood from the fact that since we have copper 2+ ion, which is a D9 system, and having a Jahn-Teller active ion, the singly occupied dx² minus y² orbital, dx² minus y² orbital is singly occupied and therefore is spin degenerate, and therefore it leads to a conduction channel in the system, and we have finite density of states. So to lift this such metallicity, we included spin polarization in our calculations. And also, since copper ion is a transition metal ion, also comes with an on-site Coulomb strength of UDD. So we chose U is equal to 6 eV on copper following the literature. And what we found that for the configuration studied 3, 4, and 6, we found that band gap reduction was 1.25 eV, right from 1.67 eV. So we have reduced the band gap now. Now to find the nature of the band gap, whether it is direct or indirect, we calculated the band structure for configuration 3, 4, and 6 along the various high symmetry points. But we found that the nature of the band gap is indeed indirect, having valence band maxima at A point and conduction band minima at gamma point in all the configuration. And such indirectness also makes charge recombination to be slow, giving time for the separated charge carriers, generated charge carriers to be separated by the polarization in the system. With this, I would conclude that our co-doping strategy of 11% concentration of Jahn-Teller active copper and tellurium ion led to a reduction of a significant 0.42 eV electron volts in the band gap, partially retaining the ferroelectric distortions, and the band gap studied was indeed found to be indirect, having low recombination rate of charge carriers, showing promises for future ferroelectric applications, ferroelectric photovoltaic applications, in fact. I would like to thank all the people who have contributed to the work, my supervisor, Professor D.D. Sharma, Professor Priya Mahadevan from SNV and CBS, my dear senior Akmal Hossain, sitting at the back, my earlier group member, Dr. Shamashish Das, Dr. Somnath Ghara from JNCSR, Professor Sundareshan from JNCSR, and Professor Gopalakrishnan from ISC. And following are the references for the work. I would like to thank Ministry of Education, Government of India for providing me the Prime Minister Research Fellowship. I would also thank Thematic Unit of Excellence at SSU ISC for the computational demands. Thank you for your kind attention.
We have time for questions.
We all know that in perovskite solar cell field, we need to design some low band gap material.
Yes.
So could you explain the shortcoming associated with the low band gap material?
In solar cells?
Yeah, in solar cells.
Low band gap materials are good for solar cells, in fact.
Yeah, they are good, but they have some shortcomings, na? Could you explain?
Shortcomings comes from stability, from in environment. I didn't get your question. What kind?
Like in band, if the band gap of material is very low, so very less amount of energy is needed for the electron and hole pair generation. So lot of energy is generated in the form of heat. So could you explain that phenomena?
The sweet band gap for a solar cell comes around to be 1.4 eV, as comes because the solar spectrum peaks at that electron volts, right? So
Yeah.
if your material comes with a band gap near to 1.4 eV or near to that, it is good. I believe that.
Okay, thank you.
Okay.
Yeah, I can
Yeah.
answer it.
So solar cell, so for solar cell material, that electron hole pair has to be separated for long time. Okay, so you are giving argue that if we make indirect band gap, then it will be for long time. But have you studied that electron phonon coupling also? Because that also can give rise to, if there is a low electron phonon coupling, that can give rise to high lifetime of the carrier also. So are you studying towards that?
Not yet, but I would like to do that.
Okay.
I have not yet studied those electron phonon couplings.
Okay, thank you.
Right. One more question there.
Talked about optimization. So what method did you use for unit cell optimization?
I didn't get you clearly.
What method you used for unit cell optimization?
LDA? Oh, LDA.
Method.
PB Sol?
No. Method meaning what kind? How did you? Is that what you're asking, or?
Yes. We did with fixing the unit cell parameters.
I quickly had another question. Your band gap you showed was about 1.4 electron volts.
That was 1.67 for pure barium titanate and came out to be 1.25 EV for the studied composition.
So experimental band gaps are larger than that.
Yes, that is underestimation by.
Sure. So you use some what kind of functionals did you use?
GGA.
GGA. Okay. Okay, if there are no further questions, then let's thank the speaker. And before we disperse, so let's.